So all of the properties about what it means to be a distance and what it means to be straight are written down here in this Geometry, Axioms, and Theorems Part 1 document. So we're just going to look at these first few definitions and this first axiom and unpack it a little bit. So I have a copy of this somewhere where I can spread everything out. So the first thing to notice here is that we have the definition of a plane, the plane, and there isn't very much to this definition. Most of what we're going to say about what it means to be a plane is going to come in the axioms we write. And so axioms are a set of properties that we say, all right, these are the building blocks of the type of mathematics we're going to do right now. So we have here the notation. We're going to use E2 or E squared to denote the plane. E stands for Euclid, and 2 stands for two-dimensional Euclidean plane. But the main thing we're saying right now is that the plane is a set of points. That doesn't sound very impressive when you start off, but that is a significant thing to say. Everything in the plane is made out of points. And then we say, all right, we're going to say that we can measure the distance between points. And so we define a distance function, and the abstract math name for a distance function is a metric. So there's a metric on the points of the plane. It's a distance function. So if there's any 2 points that are elements of the plane, so by saying up here that a plane is a set of points, down here, when I write A and B are elements of the plane, so when I write that there, I'm saying A and B are points in the plane. If I have any 2 points in the plane, then there's this number. That's a functional number. It's a function of A and B. And that gives as its output a non-negative real number called the distance. So non-negative, it can't be a negative real number. It can be 0. It can be positive. And that distance function has to satisfy these conditions, and these are the ones that we just kind of discovered when we were writing down properties that it made sense for a distance function to have. So there's that first one. If you have a point and itself, the distance from a point to itself is 0, and the only way to have a 0 distance is if they're the same point. This we're going to call the symmetric property, that the distance from A to B is the same as the distance from B to A. And this one has a name that is that pretty much all mathematicians will recognize. And it's this property that we call the triangle inequality. So what it says is if you have 3 points, any 3 points, and if you think about 3 points that form a triangle, then you're going to get, then that's going to make sense of why this is the triangle inequality. If you have the distance from A to C, that is going to be smaller than or equal to the distance from A to B and the distance from B to C. So there's my triangle, going from A to B plus going from B to C is longer than going from A to C, or in that special case where B is on the shortest path, then it might be equal. So it's either greater than or equal to. We spent a while talking about what it means to be a line segment. And so I'm just going to draw out that same picture that we had a little while ago. If you have a line segment, that line segment is all of the x's in E2, so that's the plane, and elements of the plane are points. So this is the set of points such that, so this first line is part of the set builder notation, such that, so I want all of the points that have this property. So what's that property? Well, I put on A and B, those are like my fixed points over here. And then I think about all of the different x's there could be, where if I go from A to x, and then I go from x to b, that distance is the same as going straight from A to b. So that means x is on this straight path between A and B. And so x could be any of those points where my triangle inequality is actually equal. So that's my technical definition of a segment in terms of distance function. Now we're going to take that definition of a segment and we're going to use it to define a ray and then to define an infinite line. So here's my set builder notation again. It says that if I have any point here that satisfies either of these properties, that's what or means here. If x satisfies either of those properties, then it's on the ray. So let me draw out A and B, and we'll look at those two properties. Pick 2 points to be A and B, and we say, okay, what can x do? What does a point have to do in order to be on the ray? Well, one of the things that would make it on a ray is if it was on the segment. So all of these points x that are on the segment, they are all part of the ray. All right, I'm going to switch colors. And the next thing says, if B is on the segment from A to X, so if the shortest way to get from A to X goes through B, shortest way to get from A to X has to go through B. That means X has to be out here somewhere. And so all of these things, all of these points where if I draw a shortest path from A to X, that shortest path is going to go through B, all of those points are also on the ray. So the ray includes all of these endpoints of segments out here, and it includes all of the points that are already on the segment. And so that's how I take my previous definition and build on it to get the definition of a ray. And then we're going to go and look at the definition of an infinite line. So we just want to do the same thing but in the opposite direction as well. And so that's what we get. We say, all right, my point, it's going to be on the infinite line if that point satisfies the condition that it is on the segment from A to B. So all of those x's are on the infinite line. And we're also going to include all of the x's where the line from A to X goes through B, so if the segment from A to X goes through B, then that's part of the line. And let's see if I can find another color. Also, all of the points X where A is on the line from B to X. So if I'm looking at the line from B to X and I want it to go through A, then X would be out here somewhere. So all of those points are on the line. So we take this and we get this definition of infinite line by piecing together lots of different segments. And so this is a nice, neat way to build on an earlier definition. So it's very convenient in that way. But also this is very similar to what Euclid did with lines. So when Euclid and the Greeks wrote about lines and they talked about what we would think of as an infinite line, they didn't really want to be thinking of it as infinite. They wanted to be thinking of it as indefinite. And so they would say, you can take any segment and you can extend it as far as you want in either direction. All right? And so the notion of this line is built on taking a segment and then extending that segment out in both directions. So that's a very, not only a natural, but also a very historical way of looking at what a line is.